search back in 2000 and found things I had done, and he just gave me oh, and that was the funny case where I knew the 1975 Ninham and Parsegian paper, and in my field, so the later names of the senior people. And so I figured that someone who was a professor in 1975 was most by passed away in 2000. But I tried to call him, even though I really liked that paper. It was sort of one of those funny cases, but then we've had a nice time working together. And so therefore, thank you. James is like,
you know, I don't know how verbal Roger is, but you should have seen his face and the pacing of his words when he said, I thought you were dead. About as gently as you can put it. And that was 10 years ago. Okay, so Rudy's giving you 3 really, really nice lectures on a subject that we overlap a lot in our work. So I took advantage of that to talk about something that's really quite different from the main theme of what's going on here. I'm going to talk about molecular packing, fashionably known as molecular crowding, how molecules move due to the fact that they interact with each other. We've all been brought up, of course, to know that we think as though things are dilute solutions, and then we have to correct our minds through the rest of our lives. And what happens here is I want to start thinking for molecules as being, in their real circumstance, really concentrated on what properties emerge. And you'll see lots of names of the work on the work that's going to come, but these are the good people who have enjoyed working on this subject. There'll be two parts to the talk. One is, again, something that we thought was going to be just a background thing. We measured the osmotic pressures of lots and lots of polymer solutions. The reason we did it was we were using these polymers to stress arrays of molecules, knowing how much stress we were putting on them in order to measure force versus distance curves, taking X-ray diffraction to measure the distances, and knowing how hard we were squeezing them with the polymers. One thing I decided early on was that I was never ever going to think about polymers as a subject in themselves, because people were fighting with each other all the time. They were all special cases. And it went on until I realized one day we have this huge catalog of osmotic pressures we've been using to make measurements. And I read a couple of papers about ways to think about polymers and found some very simple ways to think about polymers at very high concentrations. So I'll talk about that. One of the nice things that came out of this, and it's very active right now, if you have a so-called crowded solution, high concentration solution, the molecules pushing against each other really hard, we have discovered new classes of molecular transport that are driven by this crowding. So the second part of the talk, I'm going to show you how we're watching molecules go through channels and actually seeing times of transit as they are being driven by the forces that I'll be talking about in the first part. And then the very last bit, I'll show you some work we're doing now, where we're now realizing that in biological cells, the very condition of having a concentrated medium, the inside of the cell, creates unexpected classes of transports in biology. So it's been a new set of things all the way through. And I can say in this age of planning everything really ahead, virtually everything I tell you was discovered by accident. It took us a long time to see it because we didn't want to see it. Being good scientists, we knew what we're supposed to think, right? And tell everybody, so they'll nod politely. But virtually everything I'll tell you is something that I didn't think we would see, and it's been a long fight. So, first thing is just what do we mean by an osmotic pressure? People put on very serious faces and say, what do you mean by osmotic? So, because it can be done very complicated way. Imagine I have my fingers and I don't let the red wiry stuff go through my finger and I push down on that red stuff. How hard do I push? I'll call that an osmotic pressure. That's the work of condensing this material. And I'll show you in a minute. We use these, as I said, to calibrate solutions to measure forces. But the main idea is thinking about pressing. The way we use it, and I'll show you some data in a minute, is to take that solution where we know the pressure here, and with X-ray diffraction, measure distances between molecules, and create force distance curves. Just as a prelude, this is not what the talk's about, but maybe if I had my life to live over again, I would have volunteered to give this talk. What you see here is the pressure on an array of molecules versus the distance between the molecules measured by X-ray diffraction. And what I want everyone, including me, to understand is, how is it that between 0 and 20 angstroms between the molecular surfaces, those lines bear such a similarity to each other? Not exactly the same slope, but all essentially straight lines on semi-log paper, looking at polysaccharides, DNA, lipid bilayers. There's an entire world of behavior in here that virtually all theorists ignore. And this is the exact case where molecules get serious with each other. So it's as if the theorists are spending 95 or 98% of their time making theories about electrostatics and all these things, and I do it too. I enjoy it. But in fact, if you look at how molecules really interact, these are data. I'll say that and consider it that I've done my duty to show you data. It'd be really nice if we could begin to understand why these forces look as they do. And as I say, it'd be nice if we even paid a little attention to why they would be doing that. Just to push the point a bit, those curves refer to charged materials and neutral materials, and you see very little difference. For example, this stuff here, essentially electrically neutral. This stuff here is charged DNA. If I take the same surface, that is to say the same chemical surface as the DNA, and I make a lipid bilayer of the same type, I see that I get a parallel slope. If I rescale these data to make the difference between a curved DNA surface and express it as an interaction between planar surfaces, it overlies completely what you actually measure for planar surfaces. Nature's trying to tell us something here, and we keep ignoring it. But I just want to put that in as a due diligence to say that's what's going on. But back to the story. Essentially, we collected these data to make the force measurements I'm talking about. And here all I've done is plot the pressure for the polymers versus the concentration. Two different polymer systems, PAMs and toluene, nonpolar, and polyethylene glycol and water. And what's neat here is the same chemistry chopped up to small or one big polymer. And what you see is what I think should be intuitive to you, that if you have the same material in many small pieces, it takes more work to hold it together. And if it is at a very high concentration, you lose that difference. And that's kind of an amazing thing, that something happens up here that doesn't come into our intuition about holding molecules together. So I'm going to talk about these two systems and suggest a way to unify these data. The second thing I'm going to be talking about is membrane transport. That's part 2 of the talk, and I'll get to that in about 20 minutes. And here, what we're doing is measuring electrical current through channels, conductances of the channels where we have put molecules in the solution. And there'll be two kinds of molecules, those that go in and those that don't go in. Except that when your concentration gets bigger and bigger, the big ones will get pushed in. And there's a characteristic length that they have to satisfy to get pushed in. And that is intuitively very simple. If they're so concentrated that they're bumping into their neighbors, they will then be able to go into channels because they'll bump into a wall. A big guy outside who's interacting with neighboring molecules will go into a small space where it dilutes solutions he will not. So you think of a big molecule like this, but if he's in a concentrated solution, it can deform to push through the channel. And what you're going to see is watching molecule by molecule how they're going in, and getting the statistics of probability of entry, time of sitting in there, transport. So this is a really big adventure in learning that we're watching single molecules as they push each other. What the last part of it is, if you mix big guys and small guys, you find if the little guys have a better chance of going in than the big guys, I just do the same chemical, a colored one, this is radioisotope. If a big one cannot go in, it still competes in this space with small guys, and you see a partitioning that drives molecules in. All I can say is this is the condition in our bodies, this is how we work, this is the physical chemistry of our nature, and this turns out to be a dominant feature of transport in molecular systems, in biological systems. So I want two things to come out of this. One, I'm going to give you what I hope you can see as a unified theory, unified picture of osmotic pressure of flexible polymers. It's very simple, and I tell you the answer, you'll never forget it. And there's a logic built into the inside of fluctuations, how we take the fluctuations of the molecules and you see how they work in different kinds of steric confinement. They could be bumped by other molecules, or they could be bumped by the wall of the channel. And you can see the same energies of confinement showing up in both cases. And then this really, really fun thing that is just beginning now. Once we realize molecules can push each other, once we realize what we always knew, that materials of a mixed solution are interacting with each other, you can actually even create detectors. You can put large quantities of one material in a solution with nanomolar quantities of another, and you can begin to see how that pushes them into these channels. And we're now just beginning now a systematic design of molecular detectors. We just got some money for that, so there'll be some good story about that soon. So the first is this polymer pressure. We know the Van Hoff law, right? It's just sort of a version of ideal gas law, but this time it's for small solutes. That's obviously not in the picture there. I suggest that we start from another perspective. Imagine that that molecule is one big wiry mess, and you're having to squeeze that down. And ask you, what happens if I take some molecular scissors and I make a cut? One cut. Now you'll know that already you'll have another kind of motion because these guys could switch places, they can move independently. You've introduced a translational entropy so that you're going to be able to see a little bit of an effect of these guys moving around on what it takes to hold them together.
Are you cutting the red stuff?
The red stuff. The blue stuff, I don't know how to cut water.
The first time you showed the picture, you said you are trying to condense the red stuff by adding polymers.
Say again, please?
The first time you showed this picture, you said you are trying to condense the red stuff by adding polymers on the other side of the membrane, by pushing this stuff together.
Right. So there were two pictures. One was the red stuff pushing some other guys, and then you want to know how hard that red stuff is pushing the other guys, so you do this experiment to see what that pressure is.
Now red stuff is the polymer that's...
Now the red stuff is the polymer that was doing the pushing of the other guys before. And I started by saying, this is the calibration for those measurements, for those force measurements. Now I'm simply saying, let's take this stuff seriously. Look at the number we're getting for confining it, and see if we can understand what happens if we change the number of pieces here, but keeping the same chemistry. So there's a very large body of data that we've been going for a very long time, making our force measurements using these polymers, so we have a bunch of data to look at. And so this is the picture again, and I'll repeat what I just said. If I have very big polymers or very small polymers at high concentration, I don't see any difference in the force, in the work of keeping them together. As I have more pieces, smalls, it's more work to hold it together. I don't know if this is just seeing Roger's beautiful kids these days. I imagine kindergarten class, but you told the kids to all hold hands. It's a little different from when they're running around the house, right? So even two kids can run around the house. And, yeah, okay, so the idea here is, how do we unify all of this? How do we see this in a way that we can think of this as a picture of unifying the two ends of the curve? So there's some language that goes on in this thing, and polymer people use these phrases, and I'll just appeal to your intuition. If I have a dilute solution, basically each guy fills a space, but they're far enough apart so they're moving around independently, and the space they're filling is very small, so the first approximation are treated as though they're coming particles. As they get to something magic, and put a 5-star here, this is a concentration, the intellectuals like to tell us that you can think about these molecules as beginning to touch each other. They just fill the space, but they're not doing anything to each other. And then, when you go to very high concentrations, they kind of lose their identity. They're just a mass. And I don't know if this was one line or what kind of line it was, but you can see that this can easily turn into that. And you can see there's a kind of transition between two kinds of behavior going between two limits. Essentially, the work that's behind all this turns out you can take each of those curves with all the divergences, and you multiply by the polymer length to the 9/5 power, and you plot that on a piece of paper, and it looks like that. All of these things come together. There's this amazing thing that happens, that if you correct for the length, you take that pressure, which was big for a small guy, and multiply it by a small n. Or it's small for a big guy, and you multiply it by a big n. You get curves that look like this. This is nothing up either sleeve. This is just taking the data, and the higher powers are trying to tell you something, because suddenly each of these chemicals looks the same substance, same curve. And basically what you talk about here is kind of a trick. At very low concentrations, you have this thing called the Van 't Hoff law. As I say, it's a version of the ideal gas law. That the pressure is proportional to the concentration. Easy. And it's the weight concentration here, because we want to have weight at both ends of the curve. So you take that weight and divide by the molecular weight of the particle, so you can get a number out of this thing. At the high end, doing some manipulations, and I'll show you the manipulations in a minute, there's this very nice rule, the Descroissant law, which is known to people in polymer science, that says if I go to high enough concentration, I should be seeing the dependence that's going into the 9/4 law. I'm just curious, the following is a cultural question. How many people here have heard of the 9/4 law? Because I didn't even know about it until a few years ago. Is that common knowledge? You never heard of the 9/4 law, did you? When I was your age, I never heard of it either. Okay. What's going on is you're thinking about it as the molecules are bumping into their neighbors. They try to randomly walk while they bump into a neighbor. Then they work again, they bump into a neighbor. Each of those regions becomes a coherent domain. As the concentration is going up, they bump more often. So a given length of polymer will have more and more coherent domains. But the postulate is each of those coherent domains is acting like a particle in an ideal gas. So you have two things going on. The mere density of those coherent domains as an ideal gas thing, and the number of them because they're bumping into each other. And that's the ideology behind this 9/4 law.
Does that work? Like, if I have polymers that only have single bonds between all the carbons, so I have all the free rotations, and then I have another polymer that only has double bonds, so I can't have rotation. Those both follow that same power law?
If you cheat.
If you cheat. Okay.
If you cheat, yeah, you have to cheat, and you have to say, I'm going to define the crossover in terms of what is the flexible unit. Okay, so let's say I made a bunch of double bonds, every other one, and when I had single bonds before, you'd come out with a different density of the links in these flexibilities. But if you told me nothing else, my first answer would be, I'm just going to change the number of the independent units in a random walk. Maybe that's not really cheating, but you know, it's like degrees of freedom kind of argument. Yeah, yeah. And the other part of the question I'd like to hear, but you didn't need to ask it, is it'd be really great if we had more data to do more polymers to learn this stuff. I picked the two data sets that are that we have a reasonable amount of data. I think there's an enormous potential for learning here. We're simplifying polymers to the point where now we begin to use this, and if we start getting lots of numbers, we can answer exactly things like that. What are the coherent domains? So I can start thinking about them as randomly walking units with the right step size. Are you satisfied with my answer?
Sort of. So when you say concentration at first, I thought the concentration was of the entire polymer. But you're saying, no, that's the concentration of some subset of the polymer that's the flexible domain.
Right. Well, here this is an easy one. That's just Van Hoff law. That's an easy one. But here, what you're doing is creating a unit of concentration that's built on the concentration where they just begin to touch each other. Now, clearly, if they had different stiffnesses, you'd run into that so-called C star at a different concentration. So it's building in what you're asking into that so-called scaling factor. It's not that. It's cute. So, and honestly, sometimes I believe this, sometimes I don't. It seems too good, you know. But anyway, so the ansatz was, I'll be bold about it, let's simply add these two limits together. So you make the answer come out at both ends, and weight that by something that says this will roughly tell me where one takes over from the other. That's all. Nothing up either sleeve. It'll turn out that the simple choice, finding this thing, and you'll see it in a minute, with one parameter takes all those force curves and does that collapse that I just showed you. So you have a one parameter fit to all of those osmotic pressures to unify the force curves, which is a real bargain these days. One parameter. So that's the logic behind this thing. And you could sort of dress it up a little bit. You're going to add the two limiting forms, as I just said. And our friend Joel Cohen realized that if he did some numerology, if he sort of took the idea of that concentration where they first bump into each other and recognized how it depends on the number of units, and this goes to your question now, see what number of flexible units you're talking about, and scales with a volume that characterizes the filling of space from those units, you can actually make this transition to talk about this C star that I just mentioned, simply by knowing the concentration and the weight concentration and the number of links in the polymers. So what happens when you feed this back into here is you make a little more complicated version of the Van Hoff law than you really wanted to hear about when you're in high school. But basically it's the same idea of linearity. You've scaled the kind of concentration. It's the same thing. It's all hidden in it. You've written this guy here in a way that the polymer length comes out as a factor. And you see what's happened in this reduction here, that you have a common factor in both kinds of compression energy. So you're able to factor this out and postulate that if you only multiply by the length to the 9th, its power and length, as you perceptively say, it has to be defined recognizing chemistry, that you will get a unified statement that in these reduced concentration units, you'll have two terms. One is the Van Hoff term, the other is the Cloiseau term, and all you have to do is decide when one takes over from the other. So this is what you saw a minute ago. You do that trick on each of them. And being mathematically inclined, my talented colleagues are not satisfied. Simply you have blue polymers and red polymers looking all the same independently molecular weight. You can actually go to the next stage and monkey with the alphas. Oh no, they didn't. I didn't have it here. I'm sorry. There's another thing you can do where you can make these look the same because you rescale again on the alphas. But what's God telling you here? He's saying, is saying that you are seeing Van Hoff at one end, you're seeing de Cloiseau at the other end, and it doesn't look like it matters what the molecular weight is. And you can get intellectual about it again. You can look at the residuals of the fits. There are problems in here, in fact, if you really blow it up, but they're small. So that the alpha, if you really, really got serious about it, and you did it for each molecular weight, you'd find there's a fairly weak dependence. But when you average it all out, basically taking an average here gives you that very nice fit that you had in the previous curve. This is only trying to get alpha, give a little bit of an end dependence alpha, instead of just using one parameter. But the vast simplification endures, and being mathematically inclined, Joel Cohen couldn't stop. He had one parameter, two parameters, three parameters. But if you look at the mean square fluctuations in these cases, it's not really making a huge difference. Oh, this is the one I like, yeah. So if you take two different polymers, two different solvents, all these molecular weights, you do all this intellectual stuff to it, that's what the data look like. So I think we've all been brought up wrong, that includes me. I wish I had been brought up here and thought about concentrated polymers in the early days, and then somebody said there's this really weird thing called the ideal polymer limit, ideal molecule limit, and Van Hoffler comes out as a special case of having a concentrated polymer solution. Yeah?
So the role of parameter alpha here is just to make the transition from Van Hoff, like dilute limit, to the causal limit smooth.
Basically, yes. Basically, yes. It's simply saying that if I linear combine them, I have to have a combination. And these are the two fitting parameters for the two different polymers. I don't think there's much intellectual weight in those things. It's just a number thing. But even that can be and I don't know why Ferencz thought this was so neat. He called this redefining the virial coefficient. We can have a conversation about that. But basically, you don't think about virial coefficients anymore. All that stuff you really secretly hated. Remember virial coefficients, and then they went wrong anyway. Forget it. Okay, you just put the right answer in at the high concentration, and everything fits together very nicely. Am I the only one who secretly hated the virulence? So what have we done? We added these two forms. We extracted the 9/5. We did all this factoring that I've been talking about. And it's just really this really weird thought. If I measured one osmotic pressure for one molecular weight, if I did it with infinite accuracy, and I really believe that I'd cure everything, I could actually give you the whole osmotic pressure curve, in principle. But the point is that we're seeing the importance of this, and this is going to come in really important the rest of the talk, because what we are now realizing, these domains of coherence aren't just units of entropy of something that's trying to expand. It's going to be that they have a physical reality that they can enter small spaces. And there's this the second part talks about polymer transport, but we can unify the two things. And that seems to be a nice thing to do. But before that, if you had two sizes of the same stuff, that's the picture I show with the purple and the red guys going and not going. Think about it here. If you had big ones and small ones, the pressure of that solution would be the number of independently moving units, the Van Hoff law again. If you had pink molecules and blue molecules in a gas, you know that the pressure is going to be the pressure of the sum of the pink and the blue molecules. But this one is not going by which polymer it is. This term is just saying what the monomer density is. So there are two kinds of things going on here. Is that clear? Obvious? Yeah. So it would be that you'd have two kinds of things combining in different ways. So just remember this, that if we, this is the high school curve, right? And this is the graduate school curve. That this is what you learned as a linear dependence, this is what you learned as an interaction of finite molecules. And if you look at that, you see that there's a 300 molecular weight PhD and a 3,400 molecular weight PhD. I have failed, actually, in this talk to do the most important thing, to reward good questions. I just realized this, Rudy knows me so well, he grabbed chocolate beforehand. But what we're wanting to talk about is look at the comparison with different molecular weights. So this is the snipping argument I gave you before. Think of the pressure as the sum of number of independent units, and look at the SNPs in the chain as random positions. It's a gas of ends of molecules. And then think of the rest as one long chain. And if we can do this now with two different sizes, then we can begin to see how mixtures work. But then we can go backwards and say, gosh, if I have big guys and small guys, I have chemical potentials for all these things. I can extract now the comparative chemical potential, the work of transfer of a small guy in a company of big and small guys mixed. Now you're getting serious. Now you're looking at mixtures in more like real life and seeing what transfer possibilities there are. So let me do this very quickly because there's another half to this talk, but I just love to do this. So Rudy and I hied ourselves off to the office of Mutu, very good polymer guy, and he pointed out that we could rationalize all this simply by having Van 't Hoffy terms, log ideal. Gas terms for bigs and smalls. V is a technical notation. B stands for big, S stands for small, W stands for water. If we looked at this in the usual way polymer people do as individual molecular species, that's what you learn when you look at ideal gases. Then all these terms that depend on the amount of stuff come out from standard physical chemical polymer theory. The linear terms and square terms, because you always have to have linear and square terms. I don't know why, but you always do. But anyway, this is the important one over here, that we're seeing that a 9/4 power of the sum of the two, what I've been telling you. But now we're talking about mixing. Now we're talking about amount of stuff and number of guys. So two things here. So if we go through that reduction, it comes out very clearly that you can extract a pressure that I've been telling you about, that my pressure should now be a sum of the number of each species and a term that has amount of a species. And those of you who feel comfortable with something called the chi parameter from polymer theory, I know very few such human beings. I'm pretty sure they mean it when they say they feel comfortable. But chi is this thing that tells you how different the polymer feels next to another polymer versus how it feels next to the solvent. And that obviously doesn't know the difference between the polymer and the solvent. It's going to be a very different polymer solution than if they really keep away from each other. And that's giving you the strength of this spreading force.
Is this also the same with the alpha that you introduced before? The crossover?
Yes, 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 yes. It is exactly that. Number of guys, ideal gas, ideal solute, and then stuff.
And psi is kind of renormalizing alpha.
This is that solvent preference term, and it's built into there, yeah. So what you can do from all this is pull out, and this is the big thing that's going to happen in the next part of the talk. You can say, well, I knew what it took to squish all this stuff together when they're mixed. Now I'll get an expression what it takes to pull out a big one or pull out a small one when I have a mixture. That's important. That's going to tell us transport. It's going to tell us force on individual species. It's going to let us think better about which guy can move when. But you see, by now familiar to you terms, there is still a term that comes from an amount of monomer at 9/4 power, and then there's a 5/4 term, and that comes from essentially extracting a chemical potential of a species from what was an osmotic pressure. So again, and this is going to come in really nicely now, Van 't Hoff terms are going as individual concentrations, and these are now the combined terms. So now, I have a statement what it takes to pull one or the other kind out. I now talk about a device that watches molecules come out of a solution, and clearly the transport of that molecule is driven by its chemical potential in the bath. May I ask a cultural question? How many people hate the term chemical potential? Admit it. Okay, good, an honest man. He's gonna get another truck. You show these other guys up, jeez. Either that or he's a truckaholic. So.
It helps you lose weight.
Sorry?
It helps you lose weight.
Oh, absolutely. Chocolate is a well-known thing. It makes you jump around so much. You work it off, yeah. So the idea here is going to be, if they are pushing each other separately, if it's a different amount of work for the two to go in, but they're pushing each other from the outside the same, what kind of behaviors are we going to see? And it's obvious, I think, I hope by now. If you have a mixture, and the one gets in much easier than the other, it's that cartoon I told you already, the one that gets in easier is going to get even more. But another really neat thing is going to happen. Because I already told you that there are domains of coherence that are getting smaller and smaller. And I already told you that when they get small enough that they look like independent species, you're going to see transport from them. So that's a physicist's version of an apparatus. What looks like an electrode is an electrode. What looks like a channel is channel. What looks like I is I, or current. And what looks like V is a voltage. Okay? So that's the concept here. So by measuring the conductance and knowing whether there are blockages in here, then you'll know whether something's going in or not. So imagine this case, first of all. Let's say you have a lot of big guys outside, and they don't go in, they're not going to do a whole lot to the conductance. You're going to see that's an interesting fact that you do, but that's a little bit secondary. So there's one case like this. Your intuition's telling you something, whoops. And here are what data look like. If I take really, really small molecules, and I look at the current going through that channel, I find that there is a smaller current than what would have been if I expected from the conductivity of the solution. If I take medium-sized guys, I find there's a very noisy curve. This is gold. This is just pure gold. That noise is because the medium-sized guys are going in occasionally. And a frequency analysis of that noise is actually telling you transit times. So there's a lot of really neat stuff to learn in there. And when you go to very big channels, there's actually an increase in the conductance of the channel, but you don't see the noise. You see very little noise. I mean, not that different than that. But you'll see the odd spikes. What's going on here is a secondary effect, as I said, but I'll just say it to you so you feel better. The polymer competes with salt for the solution. So that, in fact, what's going on is that the extra salt is going into the channel. The conductance is proportional to the salt concentration. So there's a little bit higher salt concentration in the channel. You know this because you measure the activities of ions with the electrodes, and it tracks exactly with that extra thing. So there's going to be a little bit of a rise, but you'll see a much better version of that in a minute. So you can try this with different polymers, different molecular weights. The same idea, that you have a conductance. If you have a very small polymer, it goes in and the conductance goes down. You go to more concentration, conductance goes down again. Conductivity of the solution, I'll show you a graph in a second just to keep you track of this. But this is the neat one. If I have a fairly big polymer and I add it at 15%, the conductance goes up a little bit for this ion partitioning thing I was just talking about. But kaboom, when it gets to a big enough concentration, it looks like that. So, how to think about it. If we imagined that the little guys just partitioned, no trouble at all, and the conductivity of the solution is going to go as the conductance of the channel. Just to keep track like that. If we're looking at this picture I showed you already of big ones, you're going to have this guy sitting outside. Nothing really happening in there unless the ions are feeling this red stuff and don't want to go in there. But let's take a look what happens with real concentration. The bottom curve is basically as boring as I could make it. This is Krasalnikov and Bezrugov measured this some years ago. If I look at the conductance versus the concentration of the PhD, I see that there's this nice line, and it doesn't really matter if I have a 200 molecular weight or a 1500 molecular weight molecule. Let's say the open symbols. That line is not a curve fit. That line is the conductivity of the solution normalized for this graph. So basically it's saying inside that channel looks like a bulk solution. Make sense? Skeptical. You can get another piece of chocolate just because he's a little bit quiet. But now what's happening, if you go to a bigger and yet bigger polymer, I showed you the cartoon already, I showed you the data already. You see that the conductance of the channel has gone up. That was the thing I showed you. And then all of a sudden, it goes down very fast. Over this concentration range, you're pushing polymers into the channel. And you're seeing basically the occupancy of the channel from the net conductance. One of the things you do here, and obviously this is a calibration curve, if you thought about that very low molecular weight curve, this EQ partitioning curve, basically you're calibrating the channel for how much stuff is in there when there's not easy equilibration. So you can actually measure an amount in there. And here's the point of all this, that what you're seeing is a transition that suddenly these guys are going in. And when you ask yourself, what is the coherent size of that so-called blob in the polymer for the osmotic pressure we measured on that same polymer? These are the same ones as in that upper curve. You find that you've reached the dimensions of this channel as you would infer them from the osmotic pressure. So now the answer is we mixed polymers and we saw pressures. Now we mix the polymers and see how much they push each other. And this is the kind of stuff that you run into. I'm not going to say anything. I want you to look at that top graph and just read across there. The leftmost, no PG, I think we can handle that one. What's going on in the rightmost panel? You have equal amounts of big and small. This is the source of transport that I think we were all looking for. And what's going on? Obviously, the second one over in both columns is simply that guys are staying outside, and there's a little bit of that conductivity effect. The third one is what you've seen a couple of times, at least now, that the small guys go in, and they go down in proportion. The third one is something funny going on. It's when you add bigs to the outside solution of smalls, you're getting more going in than you had if you had only the 15% of the small guys. That extra pushing in is exactly this thing I was talking about, changing the chemical potential of species and driving in more materials. Right, Reed? I guess so. You guess so. I got him to open his eyes. Yeah.
So in this case, what would we expect at 30% of the smaller?
30% of the small, we're just doing just a nice equilibration. And basically, it would just be an effect like the 15% in proportion according to the graph. Yeah, that's good. That's good. But now you see this idea of what we call molecules pushing molecules. you're seeing that happening here. So what's going on is you're getting this partitioning where smaller ones, which have a little bit of a natural advantage, are being driven in even more. That's that fourth column. And this, that is that. When you go back and you calculate the chemical potentials for the species, the way I went through on the first part, and find out that that checks out with that concentration. So what we're seeing is the high concentration regime has its own ideal limit, de Cloisot thing, and that the pressure of the bath with the small correlation lengths, you can actually see driving into channels of similar dimension, and equal size particles push each other, but small guys pushed by big guys, and maybe small guys pushing back, you see extra transport. Yeah?
So the same channel, same polymer, two cases. One is 30% small, 50% big, 50% small.
Yeah.
In which case the current would be lower?
If I have 15% small and I add 15% big, then I see a lower current because the big's pushing the smalls.
Now
But
compare.
if I have pure 30% smalls, it'll be lower still. But it'll depend on the concentration outside. Because if it's a very high concentration outside, the pressure pushing them in is independent of the source of the osmotic pressure. It'll just be a numbers game, right? You'll have a partition ratio, that's the energy of transfer, but you'll have fewer guys outside, so the ratio will show up as fewer guys inside. But the work of transfer is the same. Did that make sense? Clear? So what we are thinking now is, this is Sergei Rukov, and oh, I guess I should just add this, right? So if I look at the channel conductance here, this is going to what Cedric just asked. This was that curve that said if I have small things partitioning, this is the big guys going in. But I can also think about starting to add small ones to the solution of big ones. This is exactly your question, Cedric. Good thing I had it yet. So you see that's going down linearly in the concentration. But the conductance is bigger here than it was when you had 30% small species, simply because you have only 15% outside. And it's it's a ratio that you've created, so it's fewer inside. So this all checks out numerically with the osmotic pressures and the chemical potentials of the individual species. And that's just as another version of it, just to make the point that you can do this with many kinds of mixtures, and you get these equilibrations the same way. So you're really seeing molecules pushing molecules. All of them have read physical chemistry textbooks, so they've got their chemical potentials checking out. All of them are doing what they're allowed to do with the energies that they have from being mixed. And I hesitate to go into this right now, but I'll just say it like this. We now do calculations of what is the chemical potential per monomer if we started to add small species to the big species at different preset concentrations. And that way we can come out with precise statements about what the chemical potentials are of the two species. And all this is telling you that this is the language that we think we could be talking about mixed systems and driving transport. One kind of cute thing oh, geez, this is really neat. Yeah, sorry. So this one is, look at the conductance. Let's say I have all smalls or all bigs. All bigs going because they push so hard that they, sorry, I got this small. No. All bigs go in because at very high concentration they don't know one from another. They're just these little clusters that are feeling a force. But as you go to the small end, only small ones, you get the same conductance because they're exchanging freely. But in between, something funny happens. Because if I have fewer and fewer of the big molecules, I have fewer and fewer of them going in. And what you're seeing here are these huge error bars, so-called. That's not really error. What that is Hall subject that I'm talking about, that's noise in the system, which is telling you it's a yes-no phenomenon. Is a polymer in there or not? And you measure how long he's in there, and it's diffusion, and you do all the statistical mechanics of transport. So there's a huge amount of good learning from what's going on in this case where they're pushing each other. Here, it's mainly the point that if you go from one pure to the other, there's a case in between where not so much is going in, because neither one of them has the chemical potential of concentration, the driving force of concentration. But you're seeing a qualitative difference in the behavior of the transport because of large and small. So I'm going to leave this out. Basically, it's a calculation. If I had one big polymer, how much it would fit inside and how much would dribble on the outside. I'm going to talk about something that's kind of neat. Yeah, that is one. So if you take a natural polymer, the natural pore, and indeed this is the pore we've been using in all these experiments so far. And this time, you think about a protein that's in the solution. And you ask, what are its chances of going in here? It's known this particular protein goes in and out of cells. But it's big. You look at it. It's drum scale. And it's not clear what could be a source of transport in these cases. And what I'm going to show you is, if you do the dumbest seeming thing, just add salt to the solution to change this guy so he's feeling the salt. You're going to see the effect. Suddenly, you're going to begin to see electrical signals that show you've driven a large protein into a channel just by changing the salt concentration. Let me see if I can get this going too many here at once. So the experiment is this. I won't go through all of this because the time's getting a little bit late. But if you have more and more salt in the solution, and the drop in the current is due to the presence of a protein blocking that channel, you see as you go to a higher and higher salt concentration, you're getting much more fraction of the time that the polymer's inside.
Is the protein charged?
Say again, please?
Does the protein have any charge?
Not enough so it's showing up as part of the current. I mean, the current is basically carried by the potassium chloride, and all you're seeing here is that that line gets higher and higher because you have more current density for current carriers. The salt gives it a negative conductance. That's all this part is. But the important part here is that you can now look to see the chance of it being in there and also how long it's residing in the channel. So that if you look at the time of residence as a function of the salt concentration, you find that molecules staying inside longer, not just going in with a higher probability. I'm not going to go through this quickly. I'll just say that these are 20 micromolar protein, really, really little. And yet you're getting this much of a transport effect just by the effect of salt. And what we just got a graph for this actually. We're now going to be looking at driving transport by mixing species. And it's going to tell us how transport works for large molecules through natural channels. We use salt here partly because it boosts the signal very nicely, but also it does have the effect on the protein of having this changing the chemical potential. We're going to be doing it with mixed polymers and mixed solutions also. So, let's see.
Is there any asymmetry in your model so that there's actually going to be transport from one side of the channel to the other, or is it just as probabilistic that it will come back out the same side it went in?
Is this guy going to eat the whole chocolate bar? I ask you. I ask you. And would you have asked that great question? Not this. The answer is that physical chemistry works. The symmetry doesn't really show up. I mean, okay, random walk. It goes in, and it comes out probable. Let's say it's at the middle, it'll come out with equal probability on either side. But if there's a gradient in the concentration, then indeed it'll do all the things you learned as a kid, that the chances of coming in from the left are bigger than from the right, but if it gets to the middle, it has a 50-50 chance of getting out either way, so you'll get a net transport. So you can drive. Yes, you can create directionality. And This, in fact, is what we suspect is going on in our cells. We export large numbers of peptides and small proteins, and it's not clear why they're getting out of the channels we know are there. And now we're realizing it's just the simple guts of the cell itself is likely a driving feature on this class of transport. So the procedure is going to be looking at lots and lots of different proteins going through known channels, but looking more and more with natural contents of cells to see what drives the transport. But you will get directionality, for the very reason that you have more stuff on the left than the right, and it's random once it gets in there. At least as we understand it, he goes in, and then he dithers. And the neat thing in channel transport, a little bit to one side, the longer you can keep him in there, the more he's going to have a 50-50 chance of getting out. Because it's just what you learned in random walk theory. If I start from 0 to 1, and I'm at point 2, I have a good chance of randomly walking out of the 0 end. So by the time I get to 50, halfway through, I have a 50-50 chance, and then my chances improve the other way. So if you increase the residence time, you increase the probability of net transit. Make sense? So I've learned from my friend Sergey Bezrukov, I've learned a lot of really neat random walk theory from this thing. And it's all the kinds of things that you'd see here. And to realize these are seconds of residence time, that's enormous times for a cell. I mean, these things should be in there for milliseconds or tens of milliseconds. What you're doing is stabilizing the transport by holding them in it, by molecular competition. And again, compare little salt with a lot of salt, and you see transport occurring. And I am going to just simply say this is that same graph as on the left, and these are now very carefully talking about how much time it's typically in there as a function of salt concentration and voltage. So that's just what I'm telling you. I don't want to take too much time for this. If I ran out. And basically there are these two things here. Now one is this unified picture of osmotic pressure, pushing molecules, fluctuations, and then this idea of now we're looking at we're aiming to get 50 nanomole detectors just by making channels that can sometimes allow something in there, but creating conditions that drive them in. So we think that we have a good chance of creating a physics of long residence times and also making some neat stuff. So I think that does it.